Study of electrocoagulation process for removal of heavy metals from industrial wastewater. A review. The aim of this article is to review the relevant literature that published from 2008 to 2019 on topics related to electrocoagulation within the wastewater. The main objective is focusing on electrocoagulation process for the removal of heavy metals from industrial wastewater depending on the mechanism and several affected parameters such as pH, current density, applied voltage, electrode material, time, applied voltage, inter-electrode distance, initial concentration, which have been published in journals. Keywords: electrocoagulation, industrial wastewater, heavy metal removal. 1. Introduction. Effluents from many industries are now one of the major sources of water pollution, which represent important environmental problems. These pollutants in water causes considerable damage to the aquatic environment and significant source of environmental pollution. It contains several harmful chemicals that are toxic to biological life. The reuse of wastewater has become an absolute necessity and an urgent need to develop inexpensive techniques for treatment of wastewater. A number of conventional treatment techniques have been applied to overcome this problem, such as catalytic oxidation, adsorption processes, ion exchange, biological processes, membrane separation processes, advanced oxidation processes, ultrafiltration, chemical precipitation, reverse osmosis, photocatalysis, chemical coagulation and electrocoagulation. Most of these methods are effective, although they are quite expensive and have many disadvantages and limitations. Electrocoagulation, EC, is a promising technique for removal of pollutants from wastewater due to its simple, cheap to operate, easily available equipment and environmental friendly. But it has received little scientific attention. Siringi, et.al. 2012. This process has the potential to extensively eliminate the disadvantages of the classical treatment techniques. Moreover, the mechanisms of EC are yet to be clearly understood, and there has been very little consideration of the factors that influence the effective removal of ionic species, particularly heavy metal ions, oil wastes, foodstuff, suspended particles, polymeric wastes, phenolic wastes, arsenic, textile and dyes from wastewater by this technique. Chaturvedi, et.al. 2013. 2. Electrocoagulation process. Electrocoagulation is one of the most promising process gaining attention to researcher in the present era due to its high contamination removal efficiency. It is used for both the water and wastewater treatment. In electrocoagulation process, the oxidation occurs on sacrificial anode and reduction occurs at cathode in aqueous solution when current is applied. Aluminium and iron electrode material are most commonly used due to its various advantages such as availability, their low cost. The coagulant/precipitates, such as iron and aluminum hydroxides, are formed in situ during the process, are non-toxic in nature, and have high contaminants removal efficiency. Hakazimania et.al. 2017. In electrocoagulation process, electrode material and their area, solution pH, current density and treatment time plays a significant role, whereas, presence of electrolytes and distance between electrode also can affect the process. Thakur, et.al. 2016. Mechanism of electrocoagulation. Mechanism of electrocoagulation is not fully known because of its complex reaction. The solution which to be treated by electrocoagulation is filled in the reactor. Electrodes of similar or dissimilar material are dipped into the solution and classified as anode and cathode. These electrodes are connected to the power source, through which the current is passed into the solution. When current is passed through aluminium and iron anodes, Al3+ and Fe2+ ions, respectively, are formed. At cathode, hydrogen gas and hydroxide ions are released at the same instant of time. These hydroxide ions combine with the Al3+ and Fe2+ ions in solution and formed aluminium and iron hydroxides, respectively, which act as a coagulant. Polka, et.al. 2014. Aluminium and iron are commonly used electrode in electrocoagulation process. In the iron electrode, two mechanisms have been proposed. Mohammed Hasnaini S.A., et.al. 2015, investigated that the EC process and hydrothermal mineralization methods for the removal of boron from wastewater and its recovery using Box-Benkin model as experimental setup was developed. An initial study was performed on 4 pre-selected variables: pH, current density, concentration, and time, using synthetic wastewater. In this response surface methodology, RSM, was used to evaluate the effect of process variables and their interaction on boron removal. The optimum conditions as pH 6.3, current density 17.4 mA/cm2, and time 89 minutes were obtained, and at an initial concentration of 10.4 mg/L, 99.7% boron removal was achieved. The process was effective on using RSM with a desirability value of 1.0. It has been observed that boron removal efficiency enhanced with increase in current density and treatment time, and it also increased when pH was increased from 4 to 7 and then decreased at pH 10. Adsorption kinetics study showed that the reaction followed pseudo-second-order kinetic model, evidenced by high correlation and goodness of fit. Thermodynamics study showed that mechanism of boron adsorption was chemisorption and the reaction was endothermic in nature. Furthermore, the adsorption process was spontaneous as indicated by negative values of the adsorption free energy. Treatment of real produced water using EC resulted in 98% boron removal. The hydrothermal mineralization study indicate that borate minerals recovered as recyclable precipitate from EC flocks of produced water. Umran Teskanun and Saadeddin Nacl, 2015, investigated that EC process for the removal of cadmium, CD, copper, Cu, and nickel, Ni, from a simulated wastewater by using batch cylindrical iron reactor. The various influential operational parameters like initial pH, 3, 5, 7, current density, 30, 40, 50 mA/cm2, and initial heavy metal concentration, 10, 20, 30 ppm, on removal efficiency were examined in cylindrical electrochemical reactor. It was observed from the result that removal efficiencies were significantly affected by the applied current density and pH. The experimental results indicated that the highest CD, Ni, Cu removal of 99.78%, 99.98%, 98.90% were achieved after 90 minutes EC at the current density of 30 mA/cm2 and at pH 7 using supporting electrolyte, 0,05 mNa2SO4. The experimental results revealed that the removal of heavy metal ions by this design electrochemical cell was successfully achieved. Mohammed Al-Shanak, E.T. A.L., 2015, studied that EC process for the removal of heavy metal ions, namely Cu2+, Cr3+, Ni2+, and Zn2+, from metal plating wastewater. In this study an electroreactor was used with 6 number of carbon steel electrodes having monopolar configurations. 3 of the electrodes were designated as cathodes and other 3 as anodes. The results showed that the removal efficiency of heavy metal ions increases with increasing both EC residence time and direct current density. Over 97% of heavy metal ions were removed efficiently by conducting the EC treatment at current density, CD, of 4 mA/cm2, pH of 9.56 and EC time of 45 minutes. These operating conditions led to specific energy consumption and certain amount of dissolved electrodes of around 6.25 kWh/m3 and 1.31 kg/m3, respectively. In the process of metal plating removal using EC consumes low amount of energy, making the process economically feasible and possible to scale up. The kinetic study demonstrated that the removal of such heavy metal ions followed pseudo-first-order model with current-dependent parameters. Amira Dagaz et al., 2019, investigated that EC process for the removal of divalent iron and zinc cations from water with aluminum electrodes in a discontinuous system, the effect of hydrocarbonate HCO3 ion frequently present in liquid waste and in groundwater on the EC process. For this 2 ions, the presence of hydrocarbonate strongly limits the pH variations by its buffering properties and reduces the rates of al dissolution by corrosion. Removal of this 2 cations was then shown to need longer treatment times and larger amounts of dissolved aluminum. The local pH gradients near the electrode surface with hydrocarbonate-free water was previously shown to permit local formation of stable Zn and Fe hydroxides, which actively contribute to their elimination. The presence of hydrocarbonate nearly suppresses this positive phenomenon, leading to far less efficient EC treatment. Whereas removal of zinc cations from carbonated water can be considered as their simple adsorption on the aluminum flux, Fe2+ ions are oxidized to FeO3 by air oxidation after their adsorption. Use of an overall adsorption model allowed quantitative comparison of the EC treatments, with very different adsorption parameters for the 2 metals studied. 3 parameter affected on electrocoagulation. Following are the effect of different operational parameters on removal efficiency of heavy metals from wastewater sample obtained from different industries was investigated in order to determine the operating optimum conditions which have been published in journals. Effect of pH. The initial pH of solution is one of the important factors affecting the performance of electrochemical processes as pointed by several authors. pH is a critical operating parameter influencing the performance of EC process. pH of the medium changes throughout the process, depending on the type of electrode material and initial pH. The EC process exhibits only some buffering capacity, mainly in alkaline medium, that prevents large changes in pH and a decrease of the pollutant removal efficiency. In acidic media, higher removal efficiencies are obtained. Efficiency of removal increased when initial pH of the wastewater increased. Kotiya, et al. 2003. Effect of current density. The effect of current density is an important parameter for pollutant removal within the electrocoagulation, EC, process that affects the metal hydroxide concentration formed during the method. High current density especially results in decomposition of the electrode material. With the increase of the current density higher values of removal efficiencies were obtained. The higher efficiency of removal of contaminants with increased current density was because of the higher amount of ions produced on the electrodes that promote destabilization of the pollutant molecules and the aggregation of the induced flux, while increasing hydrogen evolution. However, the increase of the current density causes higher consumption of the anode material. Current density influences coagulant dosage as well as bubble formation rate, their size, and the flux growth. Boni et al. 2010. Current density is an important factor influence the electrocoagulation, EC, process. It is found that the removal efficiency of TS, COD, and FC are increased quickly up to current density of 20 mA/cm2. This is explained the fact that the coagulant production on the anode and cathode increases at the same time as increase the current density. But, at higher current density, 25-30 mA/cm2, the removal of TS, COD, and FC are nearly constant. Mahesh et al. 2006. Effect of electrode material. The most commonly used electrode materials for EC are aluminum and iron. They are cheap, readily available and effective. Chen et al. 2000. Electrode material defines which electrochemical reactions happen within the EC system. Optimal material selection depends on the pollutants to be removed and the chemical properties of the electrolyte. In general, aluminium seems to be superior compared to iron in most cases when only the efficiency of the treatment is considered. Aluminium electrodes were most effective in removing color of the wastewater, whereas iron electrodes removed cod and phenol from the wastewater more effectively than aluminium electrodes. A joint arrangement of aluminium and iron electrodes removed color, cod, and phenol with high efficiency. Iron electrodes and a combination of iron and aluminium electrodes gave the highest arsenic removal efficiencies. From metal plating wastewater similar results were obtained for copper, chromium, and nickel removal. Effect of EC time. Reaction time is one of the most significant operational parameters for all electrochemical treatment processes, as with the increase of reaction time, corrosion of electrodes releases higher amounts of coagulant ions in the solution. An increase in reaction time improved the efficiency of phosphate removal. Bibahani et.al. 2013. Increase in electrolysis time leads to an increase in coagulant concentrations that has been reported to reduce the floc density, then to reduce their settling velocity. Zodi et.al. 2009. The EC time is an important parameter that is influential on the electrocoagulation (EC) process. Electrolysis time is of vital importance in the performance EC process. It is found that removal efficiency of TS, COD, and FC increases with increasing electrolysis time up to 15 minutes. Thereafter removal efficiency observed almost constant. The removal efficiency increased with settling time. Effect of electrolyte, NaCl, concentration. It is important to investigate the effect of electrolyte concentration since actual wastewater usually contains certain amount of salts. As the electrolyte concentration increased, the removal efficiency increased due to the increment of the electrical conductivity reaching the maximum value. However, with the increase in NaCl concentration, the removal efficiency decreased. Prasanna et.al. 2005. Sodium chloride is usually employed to increase the conductivity of the water or wastewater to be treated. The effect of electrolyte type on the removal efficiency using Fe and Al electrodes respectively in the presence of different supporting electrolytes including NaCl, KCl, CaCl2, NaF, Na2CO3, Na3PO4 were studied. Experiments were done using NaCl as it is cheap and the solution contains high conductivity, so it need low voltage for electrocoagulation and hence it is economical in industrial scale. Usually, NaCl was used as supporting electrolyte in electrochemical process and KCl is used to obtain the conductivity in EC process. Panitsa et.al. 2000. Yang et.al. 2000. Electrical energy and electrode consumption. Electrical energy consumption is a significant economical parameter in the electrocoagulation process. It can be seen that the longer contact time of the system applied, the weight of the electrode consumed in the simple EC process has been increased. The variation of electrical energy consumption increased proportionally with contact time. Effect of applied voltage. In all electrochemical processes, applied voltage is the most significant parameter for controlling the reaction rate within the electrochemical reactor. Mala et.al. 2001. It is well known that this variable determines the production rate coagulant, adjusts also bubble production, and hence affects the growth of formed flocks. The effect of inter-electrode distance. The distance between the electrode is an important variable to optimize operating costs. According to the characteristics of the effluent, the process efficiency is often improved by varying the distance between the electrodes. Effect of operating temperature. Temperature is another important operating condition which will affect pollutant removal efficiency in wastewater treatment. The turbidity removal efficiency from abattoir wastewater in the EC process increased by increasing solution. The results show that increasing temperature has a negative effect on removal. However, it should be noted that the operation of electrocoagulation, EC, process at higher temperature significantly reduced electrical energy consumption and fluid conductivity increases. Therefore, the production of hydroxide species increases rapidly then enhances pH value. Yilmaz et.al. 2008, Kittel et.al. 2011, Vasudevan et.al. 2009. For conclusion. This review was focused on the electrocoagulation method to treat the industrial wastewater by studying the mechanism, chemical reaction on the electrodes used and the affected parameters such as pH, current density, electrode material, time, electrical energy and electrode consumption, applied voltage etc. It was found that electrocoagulation technique is an effective treatment for the removal of heavy metals from industrial wastewater as it is economical and having higher removal efficiency via other conventional treatment methods. This process required simple equipment and easy operation.